Alright, so this video is going to help you with the enthalpy, entropy, and Gibbs free energy lab. It talks a little bit about the terms that you aren't as familiar with, delta G and delta S, that G is your free energy, that H is your enthalpy, hopefully you remember that from earlier this year, and that S is your entropy value, and that T represents your Kelvin temperature. That free energy basically is how much energy the work that can be used by the system to do work. It also tells you the amount of energy that would need to be done to the system if the reaction is not spontaneous. If you have a negative delta G value, free energy, then you are going to be more spontaneous, or you're going to move in the direction from reactants to products more rapidly in order to reach equilibrium. Enthalpy is your heat transferred. It's negative when you are releasing heat, exothermic. It's positive when you're absorbing heat, it's endothermic. And then entropy is disorder or chaos, randomness. If you have an increase in disorder, then you have a positive entropy value. And if you have a decrease in disorder, let's say you go from a gas to a liquid, you become more organized, or you make fewer moles of a liquid or fewer moles of a solid, then you would have a negative value for entropy. Alright, and I've shown you here kind of a chart you can use to determine when reactions will be spontaneous, when will they never be spontaneous, and then when processes will be spontaneous at lower temperatures and when they'll be spontaneous at higher temperatures. I've also given you a chart of values. The enthalpies of formation for these different substances, the free energies of formations, and then the entropy values for the different substances you used in this lab. Okay? So if that wasn't clear enough for you, I'm going to do some calculations with you that I normally go over in class. That may help some with what you're going to have to do for the lab. Okay, so that's just a quick review of those terms. Alright, and because you have to have delta G be negative, if your enthalpy value is negative, since entropy is negative T delta S, that actually becomes negative as well. So having a negative delta H and a positive delta S means you're always going to get a negative delta G. Your reaction will be spontaneous as written, regardless of the temperature. If it flips, if it's positive and negative, then it'll never be spontaneous in the direction written. If they're both positive, then the entropy term is going to give you a negative value, and at higher temperatures you're more likely to have a negative free energy value. And if both terms are negative, then it's when your reaction is exothermic, you are more likely to have a spontaneous reaction. And then you want to minimize that entropy term, so you want to use it at lower temperatures. Okay? So as I said before, the larger that value of free energy is, the more negative it is, the greater the likelihood your reaction is going to go from reactants to products until it achieves equilibrium. And so the formation values you were given, this is kind of listed for you here. For this reaction, nitrogen and hydrogen makes ammonia. And what you're going to do in the lab is similar to what you did back when we did energy with the enthalpy values of formation. Remember back then that the reactants did not have enthalpies of formation, nitrogen and hydrogen, because elements in their standard states do not require any energy to be formed. The same occurs for free energy, but every substance is assigned an entropy value just based on its state and how things are arranged in that chemical substance. So if I ask you to calculate the free energy of a reaction, you can do that by using those enthalpies of formation and entropies of formation. You can also use that to find the free energies of formation by taking the products, so 2 times the amount of ammonia, and subtracting away from it the reactants. The reactants in this particular example did not have enthalpy values, So basically it's just going to be the enthalpy of your product accounting for its stoichiometric ratio that determines the enthalpy of that reaction. So you're going to be doing that in your lab. You can also do that with the entropy values, and you'll have some of those on that chart on your lab sheet as well. Products minus reactants accounting for their stoichiometric ratios. Remember, every substance has an entropy value, so you won't have any zeros this time. I also like you to notice that this one is in joules. So what we see so far for this particular reaction is that it is an exothermic reaction, that energy is being released, and we see that there's being a decrease in this order, which if we look at the equation kind of makes sense because we're going from 4 different gases to just 2. So we're decreasing the amount of gas that we are producing. And we can do the same thing with delta G using the values products minus reactants. However, because nitrogen and hydrogen do not have free energy values assigned, it's just going to be 2 times the ammonia energy and free energy of formation, or negative 32 kilojoules. So this reaction is spontaneous as written. Because of that negative entropy value, however, as your temperature gets larger, the reaction is not as likely to be spontaneous. And so we want to say that this reaction would only be spontaneous at lower temperatures. Now, once you've calculated the delta H and delta S, you don't necessarily have to use that to calculate delta G separately. You can use the delta H and delta S to calculate it using delta G equals delta H minus T delta S. So those are the values I got from the previous slide. If I look at this equation and I substitute in my delta H value, I convert my delta S to kilojoules by dividing by 1,000 and multiplying by the temperature. I get that the delta G value is relatively close, negative 33. So whether I use the free energy equation or I use my values of formation, I should be able to calculate my delta G's, my delta H's, and my delta S's. Now, why I went through that with you, if you go back to your lab, in the questions I asked you to look at, for process 1, I asked you to tell me when you mix baking soda with vinegar, is it a physical or chemical change? And justify your answer. Write out the net ionic equation. Acetic acid is a weak acid. Sodium bicarbonate was solid to begin with. So I think the only thing you can actually ionize is the sodium acetate since it was dissolved in water. I want you to think about, based on your temperature observations, was enthalpy a positive value or was it a negative value? Was it endothermic or exothermic? And then calculate the enthalpy value using the data in table 1, just like I did in that example. Then would you expect the entropy value to have increased or decreased? Was there more disorder or was there less disorder? And then calculate what that change would have been. See if it matches up. The energy diagrams I'm talking about are the endothermic and exothermic graphs. I did not pull one of those up for you guys, so let me show you what I'm talking about. Okay, so this is representative of an endothermic graph because the product's energy was higher than the reactant's energy. An exothermic graph, the product's energy is less. So that's what I'm referring to with an energy diagram that would represent your enthalpy observations, so just your delta H. And now based on your delta H value and your delta S value, tell me what you would expect the free energy change to be. Would you expect it to be spontaneous as it's written, aka negative, or would you expect it to be positive, that you required energy to make the reaction proceed? Then I want you to calculate the free energy change using the data in table 1. You've done that separately now, and then in part I want you to actually calculate what delta G would be, assuming the temperature was around 21 degrees. So we're going to see basically how close H was to I. When I ask you what's the driving force, I'm asking you, did the enthalpy drive that reaction to occur? Did the entropy drive that reaction to occur? Did they both drive it, or did neither drive it? Okay, which one, if the reaction occurred spontaneously, helped to make that reaction take place? I would remind you to go back and look at the chart here at the beginning of the lab that talks about you want delta G to be negative. So which of those terms helped delta G to be negative? Was it the enthalpy, or was it the entropy? Was it both, or was it neither? And then in part K, is there a temperature at which this reaction would be non-spontaneous? If so, calculate it. And if there is a temperature at which it would be non-spontaneous, that would be when you have no change in delta G. So you would want delta H to equal T times delta S. So you already have a delta H value and you have a delta S value. You should be able to use those two to calculate T, if that happens. Process 2 talks about that the mass of the still will should increase. You may have seen that, you may not have. Think about why. What did the 9-volt battery provide? What would not have happened, or would the process have occurred without it? That's for you to tell me. You are told the reaction was basically still wool, which was a source of iron, and then the oxygen in the air made iron 3 oxide. Write your equation for this, and then you're going to talk about the enthalpy changes, you're going to talk about the entropy changes, you're going to make an energy diagram, you're going to talk about the free energy changes, and then you're going to talk about the driving forces again. Process 3 was just a physical change. You were doing a phase change, so you're just going to show me how ice melts, what is happening with it. And then it says explain the enthalpy change for the system observed. So remember that the water was acting as your surroundings. You added ice to the warm water. What happened to the water as the ice was added to it? Remember that if you're looking at the surroundings and you see an increase in temperature, it's because the system is losing heat to it. It's undergoing an exothermic change. And if the temperature decreases, then you are taking in heat from the system, so the system is going through an endothermic change. Okay, you're going to calculate the enthalpy change. You're going to talk about what you think happened with entropy and then calculate it. You're going to do an energy diagram again. You're going to talk about free energy. And then again, the temperature non-spontaneous, what would it be? The last one's going to be a little bit different. I'm not going to make you do as much in terms of calculations. I want you to predict what would be the sign of the enthalpy, what would be the sign of the entropy, and what would be the free energy based on what you observed. You are also told that the candle wax, that when you is a formula of C25H52. I want you to write the combustion reaction for that, remembering that the paraffin, the hydrocarbon, reacts with oxygen to make CO2 and H2O. You are told if this much heat was released. I want you to figure out what delta H would be for paraffin. I believe back in the introduction, we're going to go back and double check. CO2 and H2O are listed there along with oxygen, so you should be able to do that. So you're going to be solving for the delta H of one of the reactants rather than the delta H of the whole reaction. I'm going to get back there because this is giving you the delta H for the reaction. So you're going to solve for paraffin, and I think that's the only calculation you really have to do. This one here, is it possible this reaction could be non-spontaneous? So calculate the temperature, and then it says how is the tea candle affecting the spontaneity of the ice cube melting? Did it make it more melt more spontaneously? Did it make it melt less spontaneously? And then tell me why. Okay. If you need additional help with this lab, you are more than welcome to ask me during our 3-hour period this week.